So now we're going to look at proof by induction that looks at inequality proofs, all right? So it's a little bit different, it's slightly different, but they're the same 4 steps, it's the same process to prove anything, all right? So you need to have brushed up on completing the square and abstract inequalities. You need to be comfortable at both of those, all right? So look at the question here and I'll give an example. It's the best way of looking at it. So prove by induction that 2 to the power of n is always greater than n squared for all values of n is greater than or equal to 5. And n has to be a natural number. So 2 to the power of n is always going to be greater than n squared if you pick any value of 5, like 5 or higher, and it has to be a whole number. So how are we going to prove that? We're going to do the same method, the same steps as we did in the last few proofs. So the first one, step 1, is going to be prove true for, so we don't use n is equal to 1 in this case because it says n has to be greater than or equal to 5. So we're going to use n is equal to 5. So use the first case, all right? So we're going to have 2 to the power of 5, and then we're going to have, is greater than 5 squared. And if you do this, you're going to get 32 is greater than 25, and this is true for the first case, okay? So the next case, we're going to do the exact same thing. So we're going to say n is equal to k. So we're going to, case number 2 is we're going to assume true for n is equal to k. So that means that 2 to the power of k is greater than k squared. Alright, so now I'm going to go down and we're going to do step 3. So again, it's always the same rigorous process. So now we have to prove true for n is equal to k plus 1. N is equal to k plus 1. Alright, so now it's going to be 2 to the power of k plus 1 is greater than k plus 1 squared. So let me rearrange this a little bit. So if you remember the rules of indices, this is going to be, we're going to have 2 to the power of k dot 2 to the power of 1. So that's going to give us 2 to the power of k plus 1. So it's 2 to the power of k and 2 to the power of 1. So that's basically 2 multiplied by 2 to the power of k. And if you're confused about that, go back to our videos on indices and that's explained in more detail. So that's going to be greater than k squared plus 2k plus 1. Alright, so I just multiply that out. And again, I'm just going to do one more thing. So I'm going to say 2 multiplied by 2 to the power of k, so that's just writing that in different form, is greater than k squared plus 2k plus 1. So this next step is kind of the hard step, and is where people generally tend to get a little bit confused, alright? So it's going to be very hard for us to prove that this is true, basically, that 2 to the power of k is greater than k squared. Just because the power of k, we're going to have to bring logs into it or something like that, so that's just too complicated, and we're not going to do that. So the way to do it is, basically, see, since 2 to the power of k is greater than k squared, what we're going to do is, we're going to sub k squared into this equation here for 2 to the power of k. So I'll write that. So it's going to be 2 multiplied by k squared is greater than k squared plus 2k plus 1. Alright, so the reason being, so we know that 2 to the power of k is greater than k squared. So if we can prove this, yeah, and we know that 2 to the power of k is even bigger than this, then that means that 2 to the power of 2 multiplied by k has to be bigger than that. Yeah? So that might be a little bit of a stretch, but if you can prove that this is true, then this one has to be true because 2 to the power of k is greater than k squared. Yeah? If you aren't so sure about that step, so some people get a little bit confused, you can just sub in the thing from step 2. So you're always going to sub in whatever you assumed in step 2. You're going to sub that in somewhere in step 3 and then try to prove it to make it easier. So if you're not so sure about it, try and rewind and watch it again. But if you're not sure, then basically you can just sub it in always. So I'm going to say from step 2. So I'll put a little circle around that. I'm going to say sub in from step 2. All right. So again, if you do find these a little bit confusing, then again you can just learn the method off, and it's going to be very, very similar every single time. So anyway, now you have to prove this over here, that 2k squared is greater than k squared plus 2k plus 1. So I'm going to continue doing that over here. So sorry about the mess. So now we have 2k squared greater than k squared plus 2k plus 1. So I'm going to move everything over to this side. So it's going to be 2k squared minus k squared minus 2k minus 1 is greater than 0. So that's going to be k squared minus 2k minus 1 is greater than 0. So what we're going to do to prove this is we have to try and perfect the squares sometimes. We can't in the form it's in. So what I'm going to do is I'm going to add and take away 1. So what I mean by that is I'm going to write k squared minus 2k plus 1 minus 1, and then minus 1 is greater than 0. So we just added in this plus 1 and minus 1 to help us perfect the square. So you can do that because you're not technically changing it. You're just going plus and minus 1 and they'll cancel. So we have a perfect square here, you might see. So I'm going to continue in blue. So that's going to be k minus 1 squared, and then minus 1 and minus 1 is going to be minus 2 is greater than 0. So this might not look perfect, but this is always true because k has to always be greater than or equal to 5. So if you sub 5 or 6 or any number higher in, this is always going to be true. So we can take this as true, and that means therefore we go back up and we can say that this is true. 2 to the power of k plus 1 is greater than k plus 1 squared. Therefore 2 to the power of k plus 1 is greater than k plus 1 squared. I'm going to write that that's true as well. Alright, so that's what we tried to prove. So again, the trick is just in subbing this little thing here. So from step 2, you sub the whatever you had in step 2, you sub that into step 3 to help you prove it. And then once you do prove it, you finish off with the same statement. And I haven't rubbed it out since. Still up here. Step 4, it is true for all n is equal to k plus 1, assuming it is true for n is equal to k. And since it's true for n is equal to 1, therefore it is true for all n in a set of natural numbers. So that's how to do proof by induction using inequalities. We're going to look at another video of that if you aren't totally sure. So you can try rewinding it, try watching it again. Leave any questions for us down in the comments and we'd be happy to answer them. Because this is kind of the trickiest part here, just getting your head around that. But if you try 1 or 2 examples, maybe it might become a little bit clearer. And if not, there is always just the last option of just learning it all off and not completely understanding it, which we don't recommend, but it can be done. So anyway, join us in the next video for another proof by induction. We're using inequalities. So we'll see you next time. Don't forget to like and subscribe.